Thank you very much for your introduction, and I would like to start by thanking the organizers for giving me this opportunity to talk about my recent work. So today I would like to introduce a new concept that I decided to call non-reciprocal frustrations, where the I would like to hopefully convince you that a non-reciprocity, that is a concept that only arises in non-equivalent physics, um, is have actually a direct analogy to frustration that usually are considered in a many body context. And I would like to argue, or show that um, dynamical counterpart of what's called a order by disorder phenomenon and a spin glass like state will occur, which is known to occur in geometrical frustrated systems. So I would like to start my presentation by reminding you that in equilibrium, what's called the energy minimization principle applies. What I mean by that is, given an equilibrium system, the thing you should do is to try to compute the energy, and the minimum of the energy is what's gonna be realized as its ground state. And what that implies is that the couplings are always reciprocal, meaning Jij equals to Jji. But out of equilibrium, all these doesn't have to be true, and therefore non-reciprocal coupling can, in principle, arise. So you might think that this is a real crazy idea of considering non-reciprocal interactions, but if you look around the world, it's kind of obvious, or you'll immediately notice that that's not always true. Like if you look at the falcon, if the falcon finds a pigeon, probably the falcon will start chasing the pigeon, and pigeon will start running away. But that kind of chase and runaway motion can only arise because the falcon is affecting the pigeon in a very different way of how pigeon affects the falcon. So these kind of non-reciprocal interacting systems are actually ubiquitous in nature. So in addition to this prey and predator models, or prey and predator systems, or ecological systems, social network is also a non-reciprocally coupled network, because just because you're friends with me doesn't I'm friends with you doesn't mean that you're friends with me. So and also the neural networks are also known as a non-reciprocal network, because it's known to compose of inhibitory and excitatory neurons that are non-reciprocally interacting. So, and in a more physics context, in in a complex plasma and reactive optical matter, and as an example, it had been shown experimentally that if you immerse colloids in an active environment, generically you can find that those colloids are going to be non-reciprocally interacting. Now, so what I'm interested in is what would happen if there are many of those agents that are non-reciprocally interacting. What are the emergent collective properties of this non-reciprocally interacting matter? So just to get a taste of it, let me consider a very explicit example, which is a non-reciprocally flocking model. So what I did is I generalized the flocking Vikshek model, where and separated into two populations. So I consider population A birds and B birds. And A birds want to align with their neighbors. B birds also wants to align with their B neighbors. But the group A birds wants to align with B, but B birds might want to anti-align with A. So I allow the JAB coupling and JBA coupling to be non-reciprocally interacting, and therefore the equation of motion cannot be written in terms of the potential derivatives. So what would happen? So here's the simulation. Okay, good, it works. So in a reciprocal case, first of all, if you have high strong noise, it's obvious that you'll have this disorder phase. But when it's reciprocal and A group and B group want to align with themselves, they start to align like this. And in the low noise, but with JAB and JBA wanting to anti-align with there, it would do this anti-aligning motion. Oops, yeah. So what would happen when I turn on the non-reciprocity? So we get this, yeah, this interesting phase of where the A start to chase B, and which is clearly a non-reciprocity induced phase, in which we decided to call a chiral phase. And this is interesting in the sense that there's a spontaneous Z2 symmetry involved. So how should we understand this? Stepping back, actually, this could be understood in a more broader context of generalization of Landau theory. So what do I mean by that? Okay, so in equilibrium phase transitions, Landau theory is known to work very well. And in the Landau theory, what you do is to write down your free energy from your, in which you can restrict the form from the symmetry and look for the minimum of that. However, in a non-equivalent setup, that strategy generically does not work. However, what you can do is write down a dynamical equation of motion of the order parameter and just completely giving up writing down the free energy. So you write down all the terms that are allowed from symmetry on the right-hand side, which importantly, in general, generically cannot be written as a differentiation of the free energy. Therefore, this coupling can be have asymmetric coefficients. So if you, for example, look for the non-equivalent steady state for two-component system, this will map to a nonlinear non-Hermitian eigenvalue problem. So the result of this is a new type of transition that we decided to call non-reciprocal phase transition. So if it were Hermitian system, then all the eigenvectors have to are orthogonal. However, when it's non-Hermitian, it doesn't have to be, and there's a special point, which is called an exceptional point, where they coalesce. And what we could show was that this exceptional point is the point that marks the align phase to chiral phase transition. This is kind of a special type of phase transition in the sense that because it's characterized by the exceptional point, it kind of implies that there's a one-way coupling between the mode, which have to violate the detail bounds, and therefore there's no equilibrium counterpart. And because this is a generalization of Landau theory, this is way beyond the specific model that we consider. And actually, in this Nature paper, we consider flocking synchronization pattern formation. And in my previous work before that, I could show that even in a quantum-driven system, which is called the Polarton system, this kind of transition happens. And I would also mention that this critical phenomena that's associated with this is very special, where there's anomalously critical phenomena that is anomously enhanced fluctuation, which actually diverges at 4 spatial dimension or less. Okay, so with that introduction, and then this is not, of course, the only interesting phenomena that happens due to non-reciprocity. So there's what's called an odd elasticity appears, where the elastic moduli can have an odd part because of the non-reciprocal interactions. And also recently, people have noticed that you can have a long-range order, just like in the Taran 2 model, even in spatial 2D system, which is an apparent violation of Marvin Wagner's theorem. And way before these kind of active matter context, it had been known in the ecological systems that the biodiversity, for the biodiversity, it is crucial for non-reciprocal interactions are crucial. And also for controlling neuron systems, again, the inhibitory and exhibitory non-reciprocal interactions are playing a role. Okay, so with that introduction in mind, let me go on to my main part, which I would like to argue that non-reciprocal interaction is going to be a source of frustration. Okay, so so in order to get this intuitively, I think the best way to see it is by considering the most familiar non-reciprocity in our daily life is non-reciprocal friendship. I'm joking, but Okay. So this is so let me consider like A and B, Alice and Bob, and let me denote the distance as how close their relationship is. Okay. So so if you consider a reciprocal relationship when, like, for example, when they like each other, of course, what they should do is, they become a very good friends. Now, if it's non-reciprocal, I mean, sorry, if it's reciprocal but they don't like each other, of course, that's not the best case scenario, but it's no problem because what they should do is just run away from each other and never interact. And there's nobody that have to be unhappy. But the real problem happens when there's non-reciprocal friendship because when A likes B but B hates A, then there's no configuration that can make everybody happy. And therefore, this is a source of frustration. So, of course, the most well-known source of frustration is what's called the geometrical frustration. So those of you who don't know what it is, geometrical frustration systems are the system that cannot satisfy all the constraints desired to minimize all interactions. So the well-known example is considered like anti-ferromagnetically coupled spin on the triangular lattice. So if you put up here and down here, there's no even if you put up or down, there's no configuration that can make every bonds happy. So what's the consequence of that is that because the spins have to, at least partially compromise, and there's many ways to do that generically, this gives rise to accidental degeneracy of ground state that does not necessarily stem from the symmetry or topological arguments. So what are the consequences? I mean, there are many, many interesting phenomena that occurs because of the frustration physics, but one prime example is order by disorder phenomena. So as I said, because accidental degeneracy is not a degeneracy that's protected by symmetry or topology, very small perturbation can kill this very easily. It's very fragile. And actually, even a very small noise, like a thermal or quantum noise or weak random potential can lift this degeneracy. And as a result, some of the specific ground state will be selected. And if it happens to be that it's an ordered state, which it is in many cases actually, it means that adding a disorder gave rise to order, which is a little bit counterintuitive. So let me give an example. So let me consider a XY spin on the lattice called a Pylos-Clore lattice, which is denoted here. And this system is known to have a macroscopically large amount of degeneracy in their ground state. But what happens is that if you raise the temperature, kind of surprisingly, you'll stabilize a long-ranged order, which is counterintuitive because the temperature increases and the long-range order pops up. So now, of course, the question is are there any analogy between these two? Because in particular, I want to ask: is there this counterpart of accidental degeneracy of ground state for non-reciprocally frustrated systems, which is a source of these interesting and counterintuitive phenomena? And it doesn't look promising, right? Because you cannot define an energy in this kind of non-equilibrium systems. So what's the ground? What is the counterpart of the ground state? And also, it doesn't really even might even converge to a static state. So is there anything that you can say about it? Well, I'm going to argue that the answer is yes, you can. And I would like to argue that there is an accidental degeneracy, but not of the ground state, but of the emergent, not emergent, orbits. So, and this is due to the fact that when the coupling turns out, happens to be anti-symmetric, then there's a Liouville-type theorem that arises, and therefore you get this marginal orbits. And I would like to show that there will be a time dynamical counterpart of the order by disorder in spin glass like behavior occurs. Okay, now, so just to make it concrete, let me consider dissipative xy spin. So this is the rule of this game. So so this is the equation of motion, which is dissipatively coupled xy spins, and in generically, I can allow them to be non-reciprocal. So if it were reciprocal, then you can write down potential energy of this problem, and you can write down the equation of motion that shows that the system will drive into their minimum, and therefore, so all the you can define the potential in the reciprocal case, and you can show that for potential with geometrical frustrated case, accidental degeneracy ground state appears, which is just repeating what I said previously. Okay, so now how about anti-symmetric case, the non-reciprocal anti-symmetric case? Then what I could show was that I can show that there's a emergent Liouville theorem that emerges in this limit. So what this is saying is that there will be a conservation of the phase volume, meaning that the dynamics in this particular limit is going to be non-dissipative. And therefore, like this kind of marginal orbits where the orbits are depending on the initial condition can occur, but for example, this limit cycle where it converges to some special attractor is not going to be possible. So what I'm saying is the following. So for a two-spin XY spin system that are anti-ferromagnetic, anti-symmetrically coupled, then for example, if I start my dynamics with this particular initial state, then this A will start chasing B in this way. If I start with a different initial state, it will go perhaps in a opposite direction, but importantly with a different speed. And you can do the same thing for another initial state, and so on and so forth. And therefore, there's like a set of accidental degeneracy of orbits that are induced by these non-reciprocal frustrations. So now let me argue that there will be a order by dynamical counterpart of order by disorder, which I call time crystalline order by disorder because there is some sort of time crystalline order that emerges. Okay, so just to be concrete, just for simplicity, let's think about all-to-all coupled systems. So again, just like in the previous work, we consider group A and group B systems that are now all-to-all coupled, and they are all ferromagnetically coupled. Now let's consider JAB and JBA to be perfectly anti-symmetrically coupled. So and I have not considered any disorder yet. So in this case, because there's nothing that will prevent A groups to align, all A's to align with them, all B's to align, you can consider this as a large big spin. And therefore, the dynamics of this macroscopic spin can be understood as like just a two-spin system in the absence of noise. Okay, so all the things that I showed previously will apply. So this kind of accidental degeneracy is parameterized by the relative angle between A and B. So, like if I start this dynamics, probably this kind of circulation will happen. If I start with a different one, different dynamics occur, and so on and so forth. Okay, now what happens if I add noise? So if I add noise, what would happen is that, of course, this will get fluctuated. But the important thing is that how this kind of fluctuation happens really depends on the relative angle between this now. So because of that, how the effective coupling between the macroscopic spin is organized is going to be delta phi dependent now. And if you remember that, so delta phi dependent renormalization coupling. And if you remember that JAB being minus JBA, this anti-symmetric coupling is important for the Liouville theorem to hold, this delta phi dependence can kill that, and therefore it will make the system to converge. So these are the expression in this limit, in this particular parameter, and you can show that you will have a stable fixed point at delta phi equals plus minus pi over 2, and you can kind of see that. So this is the delta phi dependence as a function of time. And if you add noise, you can see that for different initial condition, you can see that the order by disorder happens. And it just turns out that when delta phi is finite, then if you plot the phi A or phi B dynamics, it's a time dependent state. So you can call that a time crystal if you want. Okay. So for the remaining 2 minutes, which is going to be challenging for me to look at, oh shoot. Oh well, yeah. I will go into the discussion about the spin glasses. So sorry, this should be my Hamiltonian. Oh well. So this is the if the spins have a random interaction and they're frustrated, generically you'll find that the free energy surface will be like very, very bumpy. And because this very bumping bumping free energy, it's going to be extremely difficult to find their global minimum. So as a result, you get like an extremely slow dynamics that kind of freezes with no long range order associated. So as a result, this gives rise to what's called the aging phenomena. So this is the correlation function of the spins as a function of t and what's called a waiting time tw. So tw is telling you that is the center of mass time. And so if the system is translationally invariant, there should be no tw dependence in the correlator. But as you see in the simulation, as a function of t, different tw will give different curves. And notice that the magnitude is really large compared to the coupling strength. So therefore, so these kind of this is called the aging phenomena. So the question is, can non-reciprocal frustration also give rise to these kind of glassy dynamics? And I would argue that the answer is yes. So so in order to assess that, it's very important to consider a system that have no geometrical frustration in the first place, because even if I saw slow dynamics, I can't conclude otherwise that it's purely coming from the non-reciprocal frustrations. So therefore, I consider one-dimensional random spin chain that is considering as follows. And this is a nearest neighbor interaction. If it were reciprocal, there's no frustration in this system, because if I, even with a random coupling, I can choose a unique ground state by choosing the spin chain to have this kind of configuration. So therefore, a nematic order develops, and therefore the reciprocal limits of this model have no geometrical frustrations. So just to wrap up, this is the dynamics of the non-reciprocal random spin chain. So this is the position dependence, and this y-axis is the t dependence, and I'm plotting the the angle theta with mod pi, because I'm not really interested in whether it's pointing up or down. Okay. So you can notice that some positions have like a periodic dynamics. It looks more or less like a limit cycle, while the others, it's hard to see here, it looks chaotic. And there's a like, domain of those that seems to be interacting with those. And so when I plot the time correlation function of this, it will nicely show that there's a parallel decay with this clear aging phenomena, as you saw in the usual spin glass. And but on the other hand, if you look at the spatial correlation function, you'll see that notice that this is a linear log plot, while this is a log-log plot. You'll see that this is exponential decay. So there's a short range spatial correlation. So I'm not sure if this is enough information to call these spin glass, but at least these two behaviors are reminiscent of spin glasses that can only occur in the presence of non-reciprocity. So to summarize, I pointed out the direct analogy between the geometrical and non-reciprocal frustration, and I could show that there's a accidental degeneracy of orbits that can emerge because of the anti-symmetric coupling and order by disorder and spin glass-like state arises because of that. Thank you very much.
Thank you. Thank you. Any question from the audience? Manas.
Hi. Have you tried, I mean, what would happen if you consider, like, say, a non-reciprocal, small non-reciprocal quantum system, like some interacting version of Hatano-Nelson type, but I know it's not easy to do the dynamics, but do you expect something similar to happen through those systems?
Okay, so first of all, yeah, the Hatano-Nelson. Yeah, thanks for the question. The what we need for first of all, I think it's difficult to get the what's the analogy. You're talking about the geometrical and the frustration physics, right? Or
So I'm talking about Hatano-Nelson model, but with interaction. So it's so I could call it a non-reciprocal interacting quantum system.
Right. Okay. So first, my postdoc and I are Sam Beck is have a poster on that which are exactly looking at the Hatano-Nelson model with interactions and seeing some interesting critical behavior. But I would say it's very different from what I'm talking about here. It's not about I don't see any connection to the frustration physics that I'm talking. So it's really contingent on the marginal, the Liouville theorem. There's this proof which is very easy, but there's this a conservation of the phase volume, and I'm not really sure how to think of that in quantum system. Although it's going to be very interesting to think about it in the future.
Okay. Thanks.
Thank you.
Any other question in the front here? Thanks.
Okay, thank you for a very interesting talk. And you mentioned this order by disorder phenomena, but I remember you mentioned the all-tall coupling situations. So do you also have this situation with some, not all-tall, but local couplings?
Local coupling, you're right. Yeah, so that's so you're asking what would happen if it were local interactions. Yeah, that's a very good question that I don't have an answer to. And that's so that's the thing that I will really like to go in the future, because what I'm considering here is only a one parameter delta phi order by disorder. But there are cases which can occur in geometrical frustrated case. Like this, where more dramatic things can happen, where you can start with a disorder state, and with noise, boom, you get a long range order. So I'm imagining that it should be possible. I don't find any reason why you won't have that, where I'm imagining if I can find a model where you start chaos, most of the tracks are chaos, but by adding noise, if we suddenly turn to a ferromagnetic order, that would be great. And I'm thinking of as a next step of this work to get that kind of dramatic phenomena. Yeah, thanks for the question.
Thank you.
Okay, there is a question online. Could you read it for us, please?
Yeah, so in neural networks, the non-reciprocal interactions lead to low spontaneous activity and potential for avalanches of activity with parallel distribution of size and duration. Can something similar emerge in any of the system you studied? Thanks for the question. I believe, although I'm not 100% sure, yeah, the spin glass state that I mentioned, this have this parallel decay, but of course it's not this. And which indicates kind of the scale free, the scale freeness. And I haven't looked at what you just suggested, but there may be such interesting parallel that we can observe. But at the moment, I don't have a clear answer to that. But thanks for the interesting question.
Okay, one last question.
Yeah, thanks, Leo, for the interesting question. So about this order by disorder, so you said it's a time crystal because it picks some sort of orbit in a spontaneous way. But I'm curious about the connection with the what people call usually by conventional time crystal. There they usually have a driving, and we have this frequency fractionalization. So is there like a connection between your time crystal and conventional time crystal?
Right. So I think people call those like Floquet system like a discrete time crystal.
Right.
And a big difference, of course, is that that one is breaking the discrete time transitional symmetry, while here we're breaking the continuous symmetry breaking. But there are people talking about continuous symmetry breaking, and in my understanding, perhaps it's wrong. I believe it's similar in the sense that they're looking at the limit cycle of some dynamical systems. So,
Okay. Thanks.
thank you.
Thank you very much. Thank you all to all the speakers of this session as well. Enjoy your lunch.